So let's see example number 4, which is taken from the problem 9.7 in textbook. Okay, so this question asks you to determine the stress components acting on the inclined plane AB, and you have to solve the problem using the stress transformation equations. Okay, so that means you can use the equation number 1, equation number 2, and equation number 3 to solve this problem. Okay, so here you have the element, and this is the original element. Okay, so it is subjected to 80 megapascal for the normal stress in x-axis, and then 60 megapascal for normal stress in y-axis, and 40 megapascal for the shear stress in xy plane. Okay, so let's determine what is the sign convention for all of these stresses. Okay, so we have sigma x is equals to negative 80 megapascal. Okay, why it is negative? Because the stress is acting inwards. Okay, and then for sigma y we have positive 60 megapascal because it is acting outward from the surface. And then for tau xy, it is negative 40 megapascal. Okay, why it is negative? It is because the shear stress that act on x surface, so this is x surface, so the stress act on the x surface is acting downward. So when it is acting downward, the value is negative. Okay, so this is negative 40 megapascal. Okay, so you have to determine what is the stress component when it is cut into A, B section. Okay, or you have to determine what is the stress component that acting on this plane AB. Okay, so you have to draw the diagram, the free body diagram like this. So you have this triangle shape. Okay, and then you have to draw what is the sigma x, the original sigma x, sigma y, tau xy at the bottom surface, and tau xy at the left surface. Okay, so now this is the plane AB. Okay, so this is the plane AB. Okay, so this plane AB is subjected to a new stress component, which is sigma x prime. Okay, so this is normal stress in x prime axis, and it must be 90 degree to the inclined surface. And then another stress component is shear stress in x prime y prime axis. Okay, tau x prime y prime axis, and it must be acting in parallel to the inclined surface. Okay, now let's look at the angle. Okay, so this is the original x-axis. Okay, and this is the original y-axis. Okay, so what is the theta that you are going to use to substitute into the equation? Okay, what is the theta? Is it 50? Is it 50 degree? No, it is not 50 degree. You cannot use this theta to substitute in equation 1, 2, and 3, because the theta that you have to use must be oriented from the x-axis to the new x prime axis. Okay, what is the angle in between x-axis to the x prime axis? It is here 40 degree. Okay, so 40 degree because here is 50 degree, and then 90 minus 50 degrees, so we have 40 degree here. Okay, please keep in your mind the theta that you are going to use must be measured from the x-axis to the x prime axis. Okay, the solution. Okay, so as as you can see from the previous slide, okay, so we already have sigma x, sigma y, tau xy, and also theta. Okay, theta is equals to 40 degree, for positive 40 degrees. So you are going to use all of this information and substitute into equation 1, 2, and 3 to get the new stress components. Okay, so let's try to find what is the stress component on plane AB. Okay, so you can use this equation, sigma x prime. Okay, so for sigma x prime, okay, you can just substitute negative 80 and then 60 here for sigma y, and same goes here. And then for cosine 2 theta, so this theta you must use what is the value of theta that acting from x axis to x prime axis. So we have positive 40 degree here. Okay, and then plus tau xy is negative 40, and sine 2 times 40 degree, and the answer is negative 61.55 megapascal. Okay, so negative 61.55 megapascal. And then for the shear stress in x prime y prime axis, okay, so you can use equation number 2. So just substitute the value of sigma x and sigma y and also theta, so you will get this answer, which is negative 61.99 megapascal. Okay, so basically in this question, because the question asks you to find what is the stress components that acting on plane AB,